We're going to be talking about titled Network Defender Archeology, walking through some offensive stuff with Decom, as well as our research, which is primarily defensive on top of that. Before we get going, my name is Justin Warner. I'm on Twitter. I go by the handle SixDub. I'm a principal security engineer at a company named Decom. I'm primarily on our applied threat research team, so I spend my days looking at lots of network data, trying to find bad guys doing bad things. My background's pretty varied. I spent a couple of years in the US military doing defensive work and counterintelligence work, and then I got bored with that and decided I wanted to go break into places for a living. Did that for 3 or 4 years with a small consulting company in the US. Worked on some public tools, PowerShell Empire, Veil, some of the other tools. And then after breaking into places using the same technique for 3.5 years, I decided I wanted to try to stop it for once, and so pivoted back to the blue side here. I'm speaking with Alex here.
Hi, my name is Alex Sirr. I'm a security engineer at Decom with the ATR team. Background not quite as exciting as Justin's yet. I was an intern with Iceberg and later a security engineer, and I recently graduated from the University of Washington.
With a lot of these conference talks here, it's really good to start out. Most research nowadays is always built on top of the research of other people. So I like to start out every conference talk and say thanks. This research was really inspired and driven by all the people who came out on the offensive side and pioneered these techniques and found them. So a couple of the folks are down below, Casey, Matt, Phil, and Joe. Big shout out to these guys. Our work builds on top of it. Highly recommend following them or checking them out if you get the chance. So we're going to start with a little bit of a fun story. So why are we here today? So it's the 90s. Let's take a step back. Some people might not even be born then. Alex. We have cool movies like Hackers that start to come out, making this scene popular. People start to realize this is a thing. We have really sexy computers. These things are workhorses. They never fail, never break. Really sexy operating systems. You got Windows 3.1 here. That's really the powerhouse. And then this operating system starts to grow. And it's built on top of old technologies, but those old technologies stick along. They have to be there because people built things on Windows 3.1 and they want them to work forever. One of those technologies happens to be a system called Decom we're going to be talking about. But then when you pivot into the modern day with all these youngsters, you got Matt Nelson running around, they're focused on breaking all these old subsystems. So no longer are they worried about using them for good things. They're looking at them as a way to get in. Cyber Reason has a great blog detailing some of this. A guy named Bohops does awesome research into this. This technology is now part of threat models and ways and documented methods that bad guys, such as many of the Iranian threat groups, are using to get into networks. So it all started with old technology and sexy operating systems, and now we land in despair and threats. So what are we here to talk about? We're here to talk about this. So quick video, really quick demo. Purely using a protocol called Decom and a language called PowerShell, we're able to pop a calc on a remote system. Yay, calc. It's the best thing to show. And you'll see this is all the defensive telemetry we get with Zeek and Sirr. You'll see it's a whole lot of mumbo jumbo. Nothing even says the word Decom. Nothing's logged. And Sirr, using popular open source free rule sets, you don't see any massive alerts blowing up that a well-known and documented technique was launched. And so that's what we're here to talk about today, how to improve. And you'll see this is another zoom in of that bro or Zeek log. This is just a hot mess. So you can clearly see that it's very hard to discern what actually happened here. So we're here to talk about the fact that adversaries are using this technique, red teams are using this technique. It's been around for a couple years, yet nothing rarely addresses it. So our challenge is to rise to the occasion of understand this technique, understand the protocol, which is a big enough challenge on its own, understand what makes it malicious, and then author and adapt our tools to allow us to detect it. And we're going to focus primarily on the network.
So let's go ahead and get started. This is one of Justin's favorite slides, actually. Early on, we grabbed a sampling of books on Decom, and Justin pointed out how a lot of these books were older than I am. So again, just a little bit more perspective on how long this thing has been around for. But before we can dive into Decom, we want to talk a little bit more about COM, or the component object model. And this is a language-independent model that allows applications to expose objects with functionality to a system. So what exactly does that mean? It means that objects can be written in any language of a programmer's choosing, and then other programmers can use that object also in any language of their choosing to gain functionality from it. And this is kind of a big deal, as it allowed things such as getting away from shared libraries being imported into projects, and it also made all these objects very versatile and portable, which was great. These objects are identified using something called a class identifier. These are globally unique, and so they'll be the same for the same object across all systems. And what this means is that you can use them to look up and correlate exactly what object is being used. So for example, when something like Microsoft Word is being installed, it'll install a couple objects, and if any of those object CLS IDs show up in logs or over the network, you can immediately go take that ID, look it up, and immediately correlate what object was being used. And you can start to get an idea of what's happening in an environment. And so we say on these slides that components are typically registered. There are a couple ways to kind of get around this and use COM objects when they're not explicitly registered. But for the purpose of this, we're not going to get too far into that. We also say that components implement multiple interfaces. And these interfaces are purely for interoperability. So these help to define and expose common functionality to any component that decides to implement them. And one of these interfaces of note is the iDispatch interface. And this helps to provide automation. So that means that a client can interact with an object at runtime. The iSystem Activator interface is also pretty cool, as that helps to work with the instantiation of an object. And it can either do this directly or through an iClass factory kind of pass-through. And so in our bottom image here, we show an example object. You can see that it implements multiple interfaces, and that can be any interface that the programmer chooses. However, the one interface that it must implement, which is defined by COM, is the IUnknown interface. So every COM object must have the IUnknown interface. On the side here, we have a breakdown of our MMC 2.0 application class. This is kind of used for like command line snap-ins, and it's default on Windows. In the bottom pane there, you can see that it implements a couple interfaces, and among them is IUnknown and iDispatch. So with COM out of the way, we can talk about Decom. And Decom simply is an extension of COM that allows objects to be exposed and callable over a network in a distributed manner, hence its name, distributed COM. Decom uses RPC as its primary transport protocol, where RPC is the protocol that allows services or client to access services across a network on a remote machine. And since RPC uses a client-server model, this means that code is executed on the remote server. And so this is why Decom works as a lateral movement technique. Without this code execution on a remote server, you're not going to get very far. So this is why, again, this is a workable protocol for lateral movement. So within RPC, there are a couple different calls. One of these is bind, and this allows a COM interface to be attached. And then you can use the alter context call to kind of navigate between these bound interfaces and interact with the different methods that those expose. So those two calls will come up a little bit later as well. And then after binding, messages can then be passed using very specific structures. So this is how it's going to be seen on the wire. So in the Decom request, we start out with a simple RPC header, followed by something called an ORPC this structure. And in this structure, there are a few things such as the COM version being used, any flags or extensions, and something known as a CID or a causality identifier. This allows calls to kind of be related to each other. And this is finished off by any method arguments that there may be. Decom response looks pretty similar. We have another RPC header, but instead, this time we have an ORPC that structure. This is pretty simplified and only contains the flags and extensions. And this also ends with any method return arguments. And we're going to be getting into a lot more detail about these method arguments later on.
So now that you got a brief overview, we wanted to give you another overview and focus more on the offensive side. So starting with COM broadly, COM is an extremely useful functionality that allows adversaries to accomplish different techniques or different tactics across their life cycle. It's beneficial for a number of reasons. In general, there's been the whole living off the land craze everyone's probably heard about. This kind of falls within that, living off the land in the sense that it is native in the Windows functionality. You don't have to bring anything along to use it, therefore minimizing what you introduce to the environment, which is always a good thing as a bad guy. But even more so, this is beneficial because it's so legacy and so poorly documented that it's very hard for people who might stumble on it during an investigation to understand it. So it increases that cost of people having to dive in and do research to do defense, which is never a good thing. You don't want to be in the middle of an investigation reading MSDN articles. It's a painful process. So they can be used a couple different places, as I mentioned. A lot of the endpoint-focused talks and blogs out there, such as the one by Casey and Matt at the bottom of the slide, they focus a lot on the code execution and persistence components of COM, and so we're going to let you go read that. Has anyone read that? Hands? Yeah, cool. All right, so a couple people. It's a very great talk. I highly recommend it. We're going to focus on this middle category, which is lateral movement. Now, most of you might know, but your enterprises have COM objects that enable lateral movement all over them. So all of these allow lateral movement. Pretty much the entire Microsoft Office package enables COM objects in the local Windows system that expose abilities to run command lines and load DLLs. Same thing with the MMC object, which is built into systems. So this is a problem, and it's just about everywhere. So we'll start with a demo, and the demo is to walk through how to find an abusable object. So how are researchers finding these? First, I want to show that on this system in my demo, my default implicit privilege or permission is set to administrators to allow COM launching. So with that assumption that administrators implicitly can launch COM, we can go in here, we can search for all COM objects using a tool called alleview.net for anywhere the launch permission is not set on the COM object. What that means is administrators are allowed to run these objects implicitly. You can see the MMC application is in fact allows administrators to run it through the implicit permission. So remotely, if I'm an administrator, I can use it. That's not always the case. Now, exploring this object can be quite simple. You can just load up the object using something like PowerShell and simply use the help documentation. The best way to understand a lot of these objects is just reading the help. So I'm using get member here as a command to essentially list the help, and I'm exploring the object. I'm listing the different functions involved and listing what's in play. So with that in mind, let's take the next step. Let's use that object that we just explored, which we know can be launched by an administrator maliciously. So in this demo, we essentially are going to do the first command, which is get type from program ID, essentially activating and loading that object. I'm sorry, it's instantiating an object to that object, and we're going to create instance, which actually activates it. That's when the network protocols begin. And then we're going to use a function that was exposed by that object, simple function named execute shell command, pretty blinding in the face, and we're going to run a calculator on the remote host. Again, calculator could be anything from PowerShell to any other executable you want to run, any of the law bins and other things. So 3 lines of code, native Windows functionality, code execution. Requires administrator like most of lateral movement techniques. A little bit more of a fun one is Excel. So Excel actually allows you through Decom to load up XLL plugins, which are essentially a Microsoft Office plugin in Excel. So in this case, you're not spawning any command line arguments necessarily, like you would be in the previous case. In this case, you're going to plant the DLL on the remote system using, I don't know, SMB, and then you're going to have Excel forcibly load that DLL. And the DLL is just a standard, like, standard export, standard DLL. It can have any functionality you want. It doesn't have to be formatted specifically. And when you load it, you can have it do whatever you want. So in this case, we pop calc. So again, the loading the DLL kind of gets around that command line stuff of having to use like execute shell command. Anytime you can force your defenders this crazy to post-it notes and printouts to do protocol RE, you've succeeded as an attacker. So this is after like a month of diving in on the protocol and trying to write parsers for it. Alex had literally gone mad and wearing tinfoil hats and post-it notes on paper. It was the best way he could find to figure a lot of this out.
So with that, we can get into a bit of the behavioral analysis of Decom. So Justin kind of walked through a little bit an example of how to find abusable objects, but we want to talk a little bit more about what exactly we're looking for in those. He mentioned the launch permission detail. That's nice as it can kind of allow an attacker to have a bit more of a broader scope on the users they target. So instead of targeting a very specific user who's allowed to access an object, they can target general administrators with the lack of launch permission. But by far the most important detail is that the objects must have functionality to load or execute code. Without it, again, you're not going to get very far. So looking for those specific functions that allow either DLL execution or straight command line execution, that's what attackers are going to be looking for. And in general, there are a couple different ways for people who are just curious to be looking for these. There are a few different ways to do it. Obviously, Justin showed off oliveview.net. That was a great tool for us. It's what a lot of the initial researchers on Decom use to explore this kind of thing. But for an adversary, they're not going to want to go ahead and start dropping that. So they can use a couple different methods. One of them is remote registration. So they can remotely query the registry on a remote system to kind of start enumerating and understanding what objects they have on that system, what objects they may want to target. Also, there's an awesome class in WMI called Win32 Decom application. This can be used to help enumerate all of the Decom objects on a system. So when it comes to Decom's network behavior, there are three main phases. There's the activation phase, and this is where an object is instantiated on a remote host. There's this series of optional type operations. This is basically where the client resolves any function information, understand a little bit more about how to call these functions. And then there's the execution phase, where their selected function is then executed. So we're going to go into depth on each of these phases a bit more. We're going to use our MMC 2.0 application object within PowerShell as our primary example, so what Justin demoed earlier. And so when it comes to the activation phase, these were the network functions that occurred. So first, there were these ioxid operations, and this is where the client binds to the remote RPC server. Then there was a series of authentication and authorization requests, making sure the client is good to go. Once that gets the thumbs up, PowerShell, in this case, since that's what we're using, issues an iSystem activator remote get class object request. And this basically will provide a handle to a class factory that will eventually be creating the object that they requested. And so this occurs within the iClass factory operations. So that's where the object itself is actually fully instantiated and ready to use, and then another handle is passed back so that the client can begin to operate with it.
And so each step here actually creates a whole bunch of network chatter back and forth. So these are kind of generic overview phases, but within each of these you could have anywhere from 2 to 8 packets back and forth for RPC requests and responses. So quite a bit of network chatter involved during this phase.
Yeah, so a lot of this is pretty loud. A lot of this is pretty easy to take a look at and detect. So here's a screenshot of Wireshark, specifically of remote get class object, the request. So this is what the client is sending to the server, saying, hey, I want this object to be instantiated. Within the stub data, as you can see, specifically at offset hex 01EA, we have a CLS ID. So this is the object that the client is asking the server to create for them. And so once we kind of unjumble it, there's some interesting formatting for the CLS ID. So once you piece that back together, we get down at the bottom there. So again, since this is a well-known CLS ID, we can take it to the web and try and figure out what was created. Again, for this example, we're using the application object. So of course, that's what shows up. And you can see the CLS ID matches exactly that within the packet. So this is a great option for when you want to understand kind of what's going on in your environment. You can take these, you can collect these, and then start to get a baseline of what objects are being used, and furthermore, what objects may have execution capabilities. So now there's this series of iType info operations. And the iType info is an interface that allows a client to start to query and understand how functions need to be called. So since this is happening at runtime, they need to get things such as they need to understand how a function needs to be called on the server. And this is provided automatically through iDispatch. So there's going to be 3 functions that we're going to go through. We're going to go through getFunctDesc, which is for function resolution purposes. We're going to do getNames, which is for property and function name resolution, as well as getDocumentation, which of course handles any help documentation retrieval. So here's a screenshot of what the iType info operations look like in Wireshark. As you can see, it's kind of a mess. It's pretty hard to understand exactly what's going on here. It actually took us a while to understand what these operations were. We had to kind of tie it all the way back to the iType info interface. And it's really only giving you a high level. So I can see, OK, something's happening with iType info. I don't know what, and it's going to be a real pain for me to understand at a lower level what's going on here. So this is something that we're going to return to later when we talk about how we went on to modify Wireshark to help improve the parsing capability specifically for this interface. So again, the first function that we're going to talk about is getFunctDesc. And this is used to allow a client to query for information about how to call a specific function. So some of the returns to this are things such as how many parameters a function has, what are their types, so their primitive types, as well as any return types and stuff like that. So gives the client a good understanding of how to call this function. So within the request, we provide what's known as a function index. And this is kind of in the PCAPs, you'll kind of see this counter rolling up as the client's like, I'm curious about this function, curious about this function, curious about this function, and so on. So in this one, we're seeing a function index of hex 21. And this blue section right here, these are the method arguments that I was talking about before. So pretty much you can think about anything above that is the previous Decom, like the RPC headers as well as the ORPC this structure. But that blue part is the method arguments. And then when we get to the response from the server for this specific function, again, the blue is going to be the method return arguments for the Decom response. We get a couple things. We get the full function description, which contains all the stuff that I described before and a little bit more. And we also get what's known as a member ID. And this member ID, in this case, is hex 36. And this is what we're going to be using in future calls to identify what function the client is curious about and wants to query information for. So the next function, getNames, and people generally prefer to call functions by name rather than some kind of weird hex number, weird whatnot. Names are always great for people. So that's what this function helps to do. So it'll resolve any function names and parameter names for a client. So in the request, we're going to pass in that member ID that we got from that last function, in this case hex 36. And then the response is going to give us just that. So you may be able to make out in the hex dump on the side some ASCII strings in there. Specifically, we see execute shell command, which is the command that we're interested in. And we also see the parameters that that command takes, which are command, directory, parameters, and window state. So again, this can be consumed by a client and then presented to a user. And then finally, we have get documentation. And this, of course, is sometimes users need a little bit of help understanding what exactly a function does. They want to check and make sure that this is the right function that they want to execute. This is, get all that information. So that's what this function helps to provide. Specifically, again, in the request, we're passing in our hex 36 member ID because that's the function that we're interested in. And we're also passing in a series of flags. And this will tell the server what kind of help documentation we're interested in. In this case, we're passing in saying that we want the help file and any doc strings. And again, we get a full response from the server containing full ASCII strings that can then be consumed by a client, presented to a user. And this is typically going to be seen in scripting languages. So things like PowerShell are going to use this and consume it and present it to a user. And now the final phase is execution. And so for execution, we use the iDispatch invoke function. And this will invoke a given function on the remote server. So again, in the request, we're passing in our hex 36 member ID, as that's the function we want to execute. And we're also passing in any relevant parameters that this function takes. Now remember, from getFunctDesc, we now know what parameters the function is expecting, their types and whatnot, so we have a good idea of how to call this. You can see down in the hex dump of the request, you can make out an ASCII string that's a path to calc.exe. So again, you can start to see within the package exactly where you might be able to pick out where potential adversaries might be dropping their commands. Again, calc.exe, probably not that useful for an adversary, so they can use whatever they want there. In terms of the response, it'll provide us any output that that function has. In this case, this function does not provide any output, so that's where that null string is coming from. But we do get provided a standard constant, which will tell us whether or not function execution was even successful. In this case, we get the SOK constant, meaning that we would have achieved lateral movement had we, or I guess we popped calc.exe in this case. So drawing that all together, it was kind of a lot of going through Wireshark screenshots. So pulling it all back together, we know that the member ID relates to a specific function that the client is interested in, whether or not they're executing it, such as in this case, or if they're querying for specific information, such as in the previous itype info operations. But that member ID came from the get func desk of the itype info operation. So you can kind of trace it all the way back. And you can even go further. So we know that all of these operations are relating to a single function exposed by the object's CLS ID that we requested in the very first place. So by chaining that all together, we now have a full understanding of exactly what was occurring, because we can pass back, we can even kind of replicate, we can look at the get names, we can understand what function is being run, what parameters are being passed, and relate that all the way back to an object, which is pretty cool. So with this behavioral analysis complete, we can start to define some criteria for detection. And we're going to do that with 3 different criteria sets. We're going to talk about strict criteria, and these are components of an attack chain that are required to be present for the attack chain to even exist in the first place. We also have loose criteria, and these are criteria that are in the adversary's control. So for example, we probably don't want to be looking for the string calc.exe, right? Because an adversary could change that up. They can change what they want to run. They can decide, they have full control over these criteria. And then there's also exclusion criteria. And these are things that appear to be part of a attack chain at first, but are actually benign. So we want to exclude these. So think kind of about detection tuning. So you want to tune out kind of the noise to get to the real bad. And all of these kind of work together in Boolean operations. So you can see in our diagram how we want to AND together any strict criteria we have, because we want to make sure that those exist every single time before a detection fires. Then we want to OR together any loose criteria, because these are things that could change, but we want to make sure that they're still included. And then finally, we want to not out any exclusion criteria, because we want to disregard any of that criteria before we decide to alert a detection. So returning back to Decom, these are our criteria analysis. So in terms of strict criteria, we know that activation must be done with a relevant GUID or CLS ID, so that must be present for the attack chain to exist, and that CLS ID must relate to an object with code execution functionality, because again, if it doesn't, you're not looking at much lateral movement. In terms of loose criteria, we know that the CLS ID can vary. So Justin pointed out a couple different methods of how to obtain lateral movement, and that was through various different objects. So that CLS ID will change. And there may be itype info operations depending on how the COM object is explored. So in our PowerShell example, it would actually explore every single function that an object had to offer. We also tried weaponizing this in something like Python, and that only explored the function that we decided to execute. So it can vary depending on what language the attacker decides to use. There may also be a series of iDispatch invoke depending on how many functions they want to run, specifically like their commands and their parameters are going to change. And the object's instantiation can vary. So in our example, iClassFactory create instance was used to kind of use a class factory, which the client then had to build the object off of. But iSystemActivator also offers a remote create instance, which will actually instantiate the object directly. And so actually in PowerShell, as I mentioned, it was using the iClassFactory operation. In Python, it did it directly. So it was going straight to iSystemActivator remote create instance. So that's a case where you want to make sure that you have multiple signatures that will pick up on both techniques.
And this really hammers home the importance of doing a good behavioral analysis and testing a wide variety of tools and techniques, because those little details and artifacts are really what can break detection logic and detection scenarios in the real world.
Exactly. And then for exclusions, we want to get rid of any systems that may use Decom for normal operations. Obviously, we don't want to go up flagging benign systems that are known to use Decom in their standard day-to-day use. And this is greatly aided by a large data set. So being able to look across an environment and say, OK, these are the systems that are using Decom now. These are what objects are being used. We can start to funnel those into exclusion criteria and say, when we want to start detecting bad, we're going to push those off to the side because we don't want to get many false positives off those systems.
So lots of bits and bytes. Everyone's hanging in there. So now we're going to jump into the fun part, the actually catching the bad. So I mentioned that I was a red teamer, like to do a lot of bad. This is what gets me excited now. So before we go too deep into specifics on decom detection or NSM, I want to level set some more detection concepts. So if anyone's ever heard of David Bianco's like Pyramid of Pain, or have you ever read any of the recent stuff coming out with Richard Balick or Robert Lee? There's various definitions over what defines an indicator, or what, like how detection logic should be authored. I think in general, the general acceptance is there a wide array of indicators. So what a lot of people who might not have deep threat intelligence experience would call an indicator would be like an IP address or a domain, like purely atomic indicators. And that is an indicator. It's one form of an indicator. But when you start talking like reliable detection, you have to expand that mindset to understand there's a wide spectrum of indicators. So that the atomic indicators is one. You have what I generically call simple behavioral indicators. So these would be like singular events, enriched data on top of singular events. You're really looking at a snapshot or point in time. It's behavioral because it means that something has happened. It's event-based, not entity-based, but it's not quite difficult. And this can be done with things like Zeek or Bro. Any SIMs or event automation systems can do very simple matching with queries, and that's where this falls. And then you have complex behavioral indicators. It's all the rage nowadays. You want fancy machine learning models. It's really just statistics. And you want to strap that on and know when anomalies are occurring or when novelties have been introduced to the network. And that starts getting into multi-event scenarios. And when you start looking at multiple events and having to chain those or understand behavior across events, that's a different form of indicator altogether, and it's a different form of implementation. These qualities, or these indicators, will have various qualities as well. So in general, this is a very generalized statement, which is dangerous on a stage on camera. But I think in general, the average case, complex behavioral indicators are robust because they're very abstracted, so they look at behaviors across events. The adversary would have to be a lot more careful across a longer life cycle to be able to evade. Whereas atomic indicators, they can simply just buy a new server and change their IP, or they can buy a new domain name for 29 cents on Black Friday and Namecheap, and just keep rolling these to change up. Now, that does increase the cost of their operations, but they're a little bit weaker. On the other hand, fidelity, complex behavioral indicators are so broad that it captures a wide array of activity, including a lot of potentially system administrator activity. And it's also generally not specific to an adversary. A lot of times it's specific to some behavior that an adversary is using that might be similar. Whereas atomic indicators, at least for that small time period, it's specific to that bad guy generally. Obviously, there's shared hosting environments and many complications here. So, one more concept to understand to do reliable detection, specifically with decom. So imagine this dotted line. We're going to go sciencey. Imagine this dotted line represents an adversary's technique, the attack surface. So this is a two-dimensional space which represents all the possible ways, with many infinite numbers of dots, of all the possible ways that a bad guy can implement a technique. So we have dots, and those dots represent variations of that technique. To be very applied in this case, imagine weaponizing decom attack in PowerShell and leveraging decom lateral movement in Python. Two variations, they're both decom lateral movement. MITRE attack calls them the same thing, but they're different. They have different artifacts, and they fill this attack space. Our goal as detection analysts is to form detections of many types with many different specificities and broadness levels to fill this space. We want to be able to capture every technique. One detection might cover multiple techniques. Very rarely does one detection cover all techniques. So there's a chance we might need multiple detection logic here. And then even more fun, if your detection is too broad, you start to get false positives, you fall outside the box. Or too narrow, you get white space, and white space is false negatives. Those are bad things for detection analysts. So this is kind of the science of where we want to go, and we want to use our entire technology stack to accomplish this. For NSM purposes, which is where we live and breathe every day, we're going to focus on these ones. There are three generic categories we like to talk about. So rule-based IDS, think of full packet content, snort, suricata, classic IDS that's been around since the 90s. These things look at network traffic, ingest that traffic, and then they, based on some Boolean logic or signature, they output an alert. So input is network traffic, output is an alert, not context, not packets, just the fact that something happened. And generally it's full text and etc. Then you have metadata extraction-based IDSs. This is Bro or Zeek. I keep saying Bro or Zeek. For everyone who don't know, Bro is a metadata IDS that was recently renamed due to fun conflict in the name. And so this IDS, it looks at all the network data, just like the rule-based IDS, but instead of just alerting when it sees something, it takes the time to actually parse out any elements or fields from within that network data, essentially parsing metadata. Elements or fields. It will not give you full packet content, so the idea here is that you just feed all the events that are occurring with their important or critical data points. This starts to get a little bit better than rule-based IDS because it allows you to start doing time-based analysis and full context eventing, so you can see everything happening versus only bad thing happening. Obviously, with more data comes more overhead, so you start hitting storage concerns and how do you stream this and how do you detect on it, all this other stuff. And then it gets even more complicated when you start introducing things like full content. Fantastic capability. Every network forensics person in the world will swear by, give me PCAP or give me nothing. Like, it's the only thing that's worth it. This is great. It can be extremely tough to scale. Ask your Fortune 5s or 10s of the world how much throughput they have in their network and how long they can store that. If they have a lot of money, because they're a Fortune 5 or 10, maybe they're willing to shell for it, but many cases they're not willing to. And quite frankly, the way that most people utilize this in a SOC or in a defensive scenario is they just run a metadata parser over all the PCAP anyway, and so the primary thing they're working with is metadata, similar to Bro or Zeek, and they really only go back to that full PCAP in a limited fashion. Sometimes it's even hard to go recall that full PCAP, depending on the system. So let's start with Bro or Snort. Let's look at a detection scenario for that MMC application object. So here's an example signature. In the white paper we're releasing with this talk, we actually provide a number of these. They're fairly plug and play. This is meant to be whack-a-mole, kind of. You're basically looking for the known bad or known common CSL IDs that attackers use. And so in this case, we're looking for opnum number 3. Now, opnum number 3 depends on what can be used across RPC. So opnum number 3 specifically for the MMC object represents remote get class object, the iSystem activator. In this packet, we're also looking for the characteristic meow. I kind of just put it in there because I like saying it on stage. It's a lot of fun. I don't know why this thing is in there. I'm sure it represents something, but it's always in the activations, so it makes a really good thing to include to help weed out any potential matches. And then the last one, the content, is essentially the hex string looking for that CLS ID we know for. So take this, take all the list of all the objects that people are abusing and plug and play class IDs, and you start to get a little bit context when these are used. We've had this deployed, these rules deployed in enterprises now, so we work on a SaaS platform, so we got lots of data to play with, and it actually is a very confident signature. Very simple, not rocket science, but with understanding the protocol, it gives you that context. We actually had a true positive detection on this recently with this exact signature. So it's reliable, it's proven its worth. So diving into the next one, a little bit more about Zeek or Bro. Who's used it? Zeek or Bro. All right, a little bit more in the audience. NSM people, great. So metadata parser. It has 3 key components that allow it to do what it does. First, it ingests data on the network. Those full packets then go to the eventing engine. The eventing engine in Bro essentially leverages a binary protocol specification called bin pack. These are files that define structures of what network traffic looks like. So it's a very high-level way to define a Decom request packet looks like this. A Decom response packet looks like this. So the eventing engine uses these bin packs to take these protocols and then parse them into fields. When it parses those fields, it then generates an internal Bro event that's internal to the engines. And then it has a scripting subsystem that allows you to attach to events. So I can say if a Decom request happened, run my script on all of that data. It's called a Bro script or a Zeek script. And these are handled by these event handlers, basically consume all these events and then do things. By default, what you see, the normal functionality of Bro is a whole bunch of built-in scripts that just emit logs. So you're just getting raw log data of all the fields that happen. So quite honestly, looking at this, When we first ran into this attack scenario, we were seeing this attack in the wild, and we're like, well, we obviously need to detect this. Let's see if anything detects it. And we ran it through Bro. We were kind of dumbfounded that like nothing stuck out. Same thing with Wireshark, same thing with Snort. It blew our minds that this was a thing, and it wasn't correctly parsing. And so we dived in. We tried to identify why. Why weren't we getting the data that we expected from these open source tools? And why are many people running these open source tools and probably not doing this individual unit testing, being robbed of this experience? And frankly, Bro and Zeek's an open source project, and so anyone can contribute to it, and they rely on that. They like community contribution. So the first object that we saw, or the first problem we saw, was that RPC, which is the supported protocol by default in the current Bro version, is a very high-level protocol. It's a Swiss Army knife. There's many things that happen over RPC. Everything from the service controller language to the remote registry, like everything you do on the Windows command line remotely is all mostly over RPC, including Decom. And so there are many different forms or subsystems within this generic protocol. And so what is currently implemented in the version of Zeek is the high-level generic piece. It's the RPC component. So it's the headers and the endpoint and operation that's called, but nothing specific to that operation. So a little bit more of an abstracted, not related example. Let's say I want to do a service controller action across the network. I do a create service. The only thing that's logged in Zeek is the fact that a create service happened, not the service name, not the return value, not this other stuff. It's RPC. It's not the service controller language. The other piece that was really important to understand and was important to pick out was the fact that there's entire functionality in Zeek that's commented out in the RPC parser. Like, it was attempted to be implemented, but it didn't get all the way there. I'm sure the developer, like, this is a difficult language. I'm sure he struggled and wanted to get this out. But at the time, alter context completely commented out, which means that if Decom, which it does often, jumps between interface context, every time it makes a jump using alter context, every log after that's actually not just emitted, it's wrong. It's completely wrong. It's logging the wrong endpoints to the wrong operations, because state tracking is performed only on the binds, not alter context. So important to know that if you're using this right now, you might not be seeing the accurate logs. You want to check your version of Zeek. So what we tried to do for the purpose of proof of concept here to show how we could be done is we took the easiest road we could, not necessarily the most performant or reliable, and we took every RPC request and said for every request we're going to pass the stub. So we're going to pass the stub along to the request. And so now this is not performant, this is alpha, pre-alpha, extra state on stage. I'm a researcher, not an engineer, luckily. And so this basically allows me to take scripts and do whatever I want with that stub. So I can say, if this is an SVC control operation, parse this area in the stub, and this is the new field I want to emit. And so we get to the point where I can write scripts like this, which basically say, if this is a remote get class object call, parse these parts of the stub and call that the remote class ID. So I can start to parse out individual fields within RPC. What this allows us to do, let's rerun this attack real quick. We're going to run the MMC application attack. What this allows us to do is very quickly get in and start to see when things have gone bad. So you can see here I just ran that attack, and my magic zoom in, I got the class ID of what went across the network. This is slightly improved from what I had beginning. And I also get my Sirr alert that it recognized the same class ID. So it's a little bit better. It's not perfect, but better. We can start to get telemetry over which Decom objects are being used in networks, so we can get at least a basic IDS indication of known, bad, or suspicious. And really the goal here is to empower detection. That's specific with Sirr and Zeek is empower detection, empower forensics. And so in this case, I can do one of a couple things. I can just look for all the known bad. That's the easy one. You just cross that off your list. I can sit down in 20 minutes, knock that out. But then you can start to do more fun things, like I can start to introduce statistical modeling on all of the Decom data in the network and look for abnormalities. I can start to do anomaly detection. I can start to do first observes, like the first time I ever see a Decom network appear in a network, like why is it there? And then I always thought a fun project, this is sort of a sidebar, but I always thought a really fun project would be to leverage all of this Decom eventing data to try to statistically represent human interaction with Decom versus programmatic or machine interaction with Decom. So like if I'm a PowerShell guy and I'm like in PowerShell querying typing all the help docs and going back and forth between functions, that's going to look a lot different with the iTypeInfo operations than if I'm a script that simply runs one function. So being able to pick out like, hey, a human is using Decom versus a program is, might be a really interesting problem set to use that data for.
So when it comes to PCAP analysis, Wireshark is the go-to tool for most people. I pretty much use it daily. It's one of my favorite tools, and of course it's used extensively in forensics and response situations. For its protocol parsing, it has two main components that help it along. One are dissectors, and these are built directly into the Wireshark binary and kind of iteratively take data, parse it, and hand it off to other dissectors so that they can add more information that eventually makes it to the end user. There are also plugins, and these are external components to Wireshark written in Lua. So these can be added in at any time, and they just generally extend Wireshark's functionality, and these can include protocol dissection as well. So again, we're going to return to our screenshot of the iTypeInfo operations. Again, quite a mess, very high level. We struggled for a couple hours to kind of work through and understand what was going on here when we first started looking at these PCAPs. So Wireshark handled a lot of their classic Decom operations properly. iTypeInfo completely unimplemented, and then a couple other endpoints and operations lacked full dissection. So if you recall back to the get class object, it parsed out its name and stuff, but it left the stub there. So we had to kind of dig through and find that class ID within the byte stream. So to fix this, we decided to go ahead and add on to Wireshark's existing Decom dissector. So it exists as a dissector, not a plugin. So we added a couple things to that, and then also added our typeinfo dissector along with it. And so this took a lot of protocol reverse engineering and, of course, learning how to actually write Wireshark dissectors. And this was my first time doing this. As you saw from Justin's slide, I started to go a little bit crazy in terms of how I was taking apart this protocol. So here are a couple tips for anyone who's interested in maybe getting started in protocol reverse engineering or want to try and contribute back to Wireshark. The first thing is that the existing dissectors and plugins were incredible for helping me understand exactly what should be occurring within them. So they help to provide a structure as well as show off any functions that already existed for certain operations. So it saved me a bunch of time. Also using official documentation specifically for the protocols, so things like RFCs and in this case MSDN articles were incredibly helpful as they outline exactly what a structure should look like. So things like properties and their associated types. So you could begin to pick out where things need to be within or what things should exist within a series of bytes. And then by using multiple variations of an attack, so changing up parameters, or I even implemented a custom comma or decom object so that I could change like the number of parameters I had, the types of the parameters. You can start to pick out known properties. So you can say, okay, these are probably the parameters. This is probably an array showing all the parameters here. This is the length of the array, such and such. And this is the result. So now you can see that the iTypeInfo operations are fully parsed and dissected. Not only can you tell exactly what operation is occurring, but also you get a full breakdown of what's occurring within them. And this is something I'm going to be trying to contribute and make a pull request to Wireshark when we get back.
So we're network people. We obviously stood up on the stage a bunch, talked all about the network, but we'd be silly to not mention Endpoint. Simple fact of the matter is bad guys evade, just like they know that people are watching, they try to evade. So let's say they're focusing purely on evading the network. Anyone who's doing detection on an enterprise scale really needs to rely on both your network data and your endpoint data and your application logs and the whole mix of that. And so we'd be negligent to not talk at least a slide about Endpoint. Do note that there are ways for adversaries to evade. Alter context is an obvious one given the current implementation. Packet privacy, you can actually force the packet contents of RPC to be encrypted so we'd miss all the underlying decom stuff. I'll note here though that in most networks, I think almost all the ones we monitor, like this isn't a thing yet. It's coming, but it's not a thing. So if you start implementing packet privacy as an adversary, it's actually an indicator. Like you turning on encryption stands out to me because it's not normally there and it's not the default domain setting. So command line is king for Endpoint on this stuff. I'll note that anytime you launch a decom process, so let's say we're using an outlet com object object, it spawns over SVC. It spawns under the Decom launch SVC host. So it is very easy to say which Decom object or which processes are spawning under this host and which ones should be and should not be. So like Outlook probably shouldn't be spawning random Decom services all the time. And then another one is a lot of the Office applications have command line parameters -embedding or /automation for their Decom objects when they start up. So it could be a good thing to go look for. And this is implemented by the actual underlying services themselves. So we're running short on time. Big takeaways we want you to walk away with. The detection, the repeatable and detection process to evaluate your tools. Emulate that adversary, look at those components that are involved, conduct an analysis to identify strict and loose components, build detection criteria around that, test it out, deploy it, and gain advantage. If your tools don't allow you to do it, better the tools. That's what they're there for in many of the open source cases. And then the non-Decom specific takeaways, kind of that URA mission, like we're there to detect bad guys on the defensive side, and if you're a red teamer or a pen tester, you're there to help us detect bad guys. So it's all a big happy community. Work together, understand the threats, and figure out how to stop them. Understanding is a key component that you have to start with. You have to understand the protocols, you have to understand the threats. So I think we have 1 minute, so we might be able to get a question in. Luckily, only one question. Yes. Or you guys are holding back. Appreciate that.
So, just a question, how would you guys take this approach in a kind of a cloud environment? Because obviously this is very network-centric and you can get a lot of stuff off there, whereas if you're going to someone else's environment, those things aren't exposed to you with the same kind of methodology as you would.
That's a great question. The question was, how do you implement this in a cloud environment, TLDR, like, you have to worry about other people's environments too. So 2 answers to that, or 1 explanation. There are network monitoring capabilities that are in cloud native capabilities, but they're flow. So you don't get, not only do you not get RPC level data, you're not getting Decom data, you're not getting any of the bottom-neath. You could look at port numbers, you could look at flow behaviors. Most of these cloud environments are server lands, and so like, should your servers be even exposing this? Do you see connections to them, et cetera? That's a very Wild West approach. In practice, I would say that'd be very difficult. Flow data is actually very hard to do reliable detecting around. There's another approach, which is mini vendors. I will not do too much vendor pitching. Mini vendors sell technology that get you full PCAP data in the cloud environments. There are pluses and minuses to that in throughput and bandwidth and processing power and stuff. But there are ways to gain full PCAP contents inside the cloud environments. It might be something you select on your Crown Jewel servers, or on a small subset. But we've seen success with that technique and gaining some visibility. And that is it for me. I am up on time. Thank you guys for attending.